profesor Mike Shub de la Universidad de la Ciudad de Nueva York. Ya casi lo podemos considerar como invitado frecuente de nuestro instituto. Y hoy nos va a hablar sobre homología y caos.
Thanks, Santiago. It's a pleasure to be back. I must say, just even when I got on the metro this morning, I was already in a good mood. Even though it was very crowded and I had to push my way in. Okay, so let me start with just a reminder. Gradient vector fields. So you have some manifold, which I'm always going to have a compact manifold, and I have a function on it. And then you want it to have the following properties. H has only finitely many critical points. And they're all non-degenerate. Critical points, you have the in manifold and the out manifold. So you have the in manifold. If the index is I, its dimension, dimension m equals little m. So then if the index is I, its dimension is n minus I, and the out manifold. Well, actually, I'm going to take minus the gradient. So let me say minus the gradient vector field. Okay. I like for things to go down the height. Minus the gradient vector field, the in manifold has dimension n minus I, the out manifold dimension I, they are all transversal. And that means that if they meet, that I must be bigger than J. They can't be equal because they intersect in an orbit which is one dimensional. So you have the, they're all transversal in the following sense. All out manifolds, all out, transversal to all in. But they intersect in orbits if they intersect. These things are invariant under the equation. So they intersect in something dimension 1. So it means that the in manifold, the out minus in is bigger than 1. And that means the out is bigger than the out minus 1, right? Because they add up to n. So the index is going down if there's an intersection. So here's a picture. Presumably these are the critical points of index 1, these are index 2, there's one in here, index 0. These are supposed to be the handles of the manifold that correspond to those critical points. So there's one handle, and then there's another one handle here, and there are two handles, two-dimensional outgoing. So that's the picture for gradient vector fields. And if I, the Morse inequalities here, which say that if you look at the handles of index I or below, and you take an alternating sum, that alternating sum is bigger than or equal to the alternating sum of the Betty numbers in those dimensions. And the reason is, well, one reason you could see or think about is that this gradient flow is transversal to the level surfaces. So it's preserving the union of the handles up to index I is preserved by this flow. So then you could look at the homology of the relative things, the index I modulo index I minus 1. So that will give you have a kind of filtration for the manifold, and in between each level of filtration, you just have the handles of index I. And that relative homology now is complex for the manifold. So that's how you can see the Morse inequalities here. So now, I'm not really sure, entirely sure about the history here, but Smale met Mauricio Peixoto at some point. And Peixoto was interested in dynamical systems. And I guess he explained to Smale his work on dynamical systems and his classification theorem in 2 dimensions. And then Smale went ahead and defined an analog of this, which was dynamic. So now there's Morse-Smale dynamical systems. Diffeomorphisms. And it's the same. So you say F takes n to m. And the first issue is finitely many realities. All hyperbolic. Second piece is the out manifolds are transversal to the in manifolds. So each hyperbolic periodic point looks just like a critical point of a function that's non-degenerate. You have a critical point of a function that's non-degenerate. It means that there are no zeros to the real parts of the eigenvalues. That means the linear part splits up into 2 spaces, one that's being mapped into itself, the other one's being mapped over itself. And then the theorem is that the nonlinear situation is exactly like the linear, except now you don't have linear manifolds, but something approximately linear, some differentiable submanifolds, and the points of going out on one and going in on the other, and if this dimension is I, n minus I. Again, you have index I for the manifold. The picture, the local picture, is exactly the same. So we have finally then you want periodic, but now you want the in manifolds and out manifolds. Are again transversal. And now you have to add a condition that was automatic here, is that the union of ins equals union of outs equals the whole map. And the first theorem, I think that's now proved on this, in this context, was that there's, again, Morse inequalities. The same inequalities are true here that were true for the gradient vector fields. So Morse inequalities still hold. Same. I must say, this, these systems still have a filtration, which looks kind of the same, but there's a big difference here. When the in manifolds and out manifolds intersect transversally, if one is dimension I and the other is dimension n minus I, they can intersect in points. There's no restriction that the orbits be, that they intersect in one-dimensional objects now. So now, you have to have just I is bigger than or equal to j. And you can have that. You can have something that looks like this. Here's an out manifold. Here's an in manifold. Here's another in manifold and an out manifold. And this one comes across and intersects that one in a point. Well, not one point, because they're going to be invariant by the dynamics, so this has to keep intersecting. So the picture is a little more complicated. It's not so clearly cellular to begin with. And instead of using some kind of cellular homology theory, Smale used some kind of check homology theory with respect to the closure of these manifolds, which now still have an order on them. So you've still got Morse inequalities, but the situation is more difficult. The filtration, you can't get a filtration that isolates all the I handles, or all the periodic points of index. Of course, they don't have to be fixed now either. For example, if you have a manifold with a symmetry, it might be commuting these points. You have them fixed, commuting these two. So no longer do the points have to be fixed, they might be commuted around. So you might get periodic orbits that aren't fixed, and you might have intersections of in manifolds and out manifolds that are more complicated than in the gradient picture. So now I'm going to recommend, so this is the story around 1962 or so. Smale was proving the Poincare conjecture at the time. At some point I asked him if there was a big connection in his mind between, he said no, but I don't believe it. And then he was working hard on dynamical systems. He made some bad conjectures, like he thought maybe according to Peixoto's theory, in 2 dimensions, he proved, well, maybe in 1 dimension. For vector fields in 2 dimensions, Peixoto had proven an open density theory. So Smale thought, oh, maybe these Morse-Smale things are open and dense in every manifold. And well, he got a letter from, the names are escaping me now, the guy at MIT who's differential equations. He got a letter from him about old work that was showing the Van Hall equation, because it had infinitely many periodic orbits. And so then Smale looked at it, thought about it, drew the picture that turned into the horseshoe, and now you saw they were okay. Possibilities of having diffeomorphisms with infinitely many periodic points, and in a stable fashion they were stable. So no longer could you think that the typical picture is Morse-Smale. Maybe the typical picture has to include infinitely many periodic points, horseshoes, Cantor sets, the invariances of the Cantor sets with complex dynamics on them. So that That was the start of a big change, I think. And I recommend that everybody read Smale's 1967 article in the Bulletin of the American Math Society called Differentiable Dynamical Systems. It's really a masterpiece of seeing how a lot of mathematics fits together and impacts each branch and other branches. And gives a unifying picture for dynamics that's quite amazing. I think it's been reprinted recently, maybe with comments, so that's probably better to look at a more recent copy. In that article, he asked what restrictions are there on Morse-Smale systems. Yeah. Oh, actually, this one doesn't move. Oh, I thought the bottom one moved. All right, too bad. Which one should I? I'll put down this one. What restrictions let's say diffeomorphisms. And he said, are there any beyond that the Lefschetz numbers are bounded? Lefschetz, or maybe like that, maybe. So of course the Lefschetz numbers have to be bounded because these periodic points have no eigenvalue that's modulus 1, they're hyperbolic. They are all transversal for all periods. So no matter how far you iterate it, they stay transversal. Transversal periodic points have index 1. So the right-hand side of the Lefschetz formula is bounded by the number of periodic orbits you have. That number is finite. So the Lefschetz numbers can't go to infinity. Okay, so the Lefschetz numbers have to be bound. So he said, is there any condition, restriction beyond that? Frankly, I thought that would be amazing. Because you take any f, say f n to n, and you product it with rotation. This one, if this is an irrational rotation, it has no periodic points, because it has no periodic points in the S1 factors, rotating by an irrational. So the Lefschetz numbers are all 0. And that's seen in the homology because each eigenvalue appears now in 2 dimensions with a different sign. So the Lefschetz numbers on homology cancels out just because of the Kunith formula. So the Lefschetz numbers are 0 even. But that's like crazy. What if M were a complicated diffeomorphism, one of these horseshoes? So you're now going to take it and you're going to product it with the rotation. Now instead of having a cancer set of periodic things, you have a cancer set of circles. They're all invariant. They're all hyperbolic. You're not going to get rid of them. Not by a small perturbation anyway. So certainly, if you're going to do this, it would have to be gross. So this is made it seem unlikely to me. And in fact, I thought it would be a disaster because somehow we would lose the relation between topology and dynamics. How come this one moved? Oh, because I pulled it down. Okay. So here's the theorem that I proved at that time. If F is Morse-Smale, then all the eigenvalues of the induced map of homology are roots of unity. And then, of course, modulus 1. So it couldn't be. Because if you took something with an eigenvalue that was not modulus 1, you product it with a circle, it stays there, but it repeats in 2 dimensions. So if it's not a root of unity to start with, it's not a root of unity anymore. So it shows you that if you take something with complicated dynamics, and it shows up in the homology theory of the map, for example, maybe the 2-1-1 map. Oh, that's too easy. Then it can be homotopic even to a Morse-Smale diffeomorphism. All right, well, there was another thing that was happening around the same time here, and that was in this unification process, Smale had defined a class of diffeomorphisms called axiomae no cycles. So it unified things like the geodesic flow and manifolds of negative curvature, diffeomorphisms of the Torres with like the famous Tom diffeomorphism, 2-1-1-1. These had hyperbolic structures. I don't want to define them. So Smale had an axiom A, no cycle. Diffeos, these were diffeomorphisms that had hyperbolic structures on their non-wandering set, and they could be filtered. But the non-wandering sets could have pieces, a finite number of filters, and pieces could be horseshoes, or things very, very complicated like that. So it was like Morse system in the sense you have filtration, but what's there is not a point, it's some extremely complex dynamical object. And what the theorem was, these were what was called, had a certain stability property, which was called omega. So I think this was like an evolution. Smale thought Morse-Smale, open and dense. The general dynamics was Morse-Smale. Wrong. But Morse-Smales are structurally stable. Okay, well maybe structurally stable are open and dense, but they have more complicated dynamics in the piece. No, structurally stables are not open and dense. Maybe omega stable are open and dense in the space, or residual at least in the space of dynamical system. And so no, sometime, I forgot what year, no, these systems are not open and dense in the space of dynamical system. I think it must have been around 1971. There was a conference in Brazil, or in Rio. And so I raised the question, is it even true that every diffeomorphism is isotopic to a structural stability? Maybe there are global topological obstructions. So I was thinking about that, talking to Bob Williams about it a little bit, thinking about the Torres, how you could isotopic diffeomorphism of the Torres, maybe to preserve the handles. I ran into Steve and told him about that, and the next day he had solved the problem. And he said he wrote a little paper saying he had run into me on the beaches of Rio on a Sunday afternoon, and I told him about the problem, and here was the proof that every diffeomorphism is isotopic to a Morse-Smale, to a structurally stable diffeomorphism. I got the paper. I went in to see him. I said, Steve, you're getting conservative in your old age. Old age must have been, I don't know, 40 something. You're getting conservative in your old age. He said, what? What do you mean? I said, you said Sunday afternoon. I mean, you have a right to be on the beach on Sunday afternoon, even according to these people who were criticizing you for doing mathematics on the Ile-de-France, and then saying that you had done some of your best work on the beaches of Rio. So there was a huge, when this controversy happened, which was largely connected with politics at the time, there was a huge uproar. So I said, look, now you're making it safe, you're saying Sunday. He took it out, took the Sunday. So there was his method of proof, which had something to do with the oh dear. Oh well. So the story about gradient dynamical systems goes, the gradient functions on manifolds and their critical points goes a little further, right? And so then there's the theorem of Smale. It's called the H-equilibrium theorem. I'm going to state it a little differently. He says, first of all, gradient function as described above gives a chain complex for the homology of the manifold. That's one side. So it's like 0 goes into C0, C1, Cm. 0, this is a chain complex, and you get it by looking at these relative homology groups. Okay, so that gives you the chain complex for the manifold. But then he says, if dimension n is bigger than 6 and polygon n is 0, then if you're given a chain complex which commutes the homology of n, it is the chain complex of the gradient. So in particular, if it's the homology of the sphere, there is a function with only a minimum and a maximum. I think 1971, 72, I was in Santa Cruz. And I was trying to think of, now I've got this theorem that Morse-Smale diffeomorphisms have only roots of unity as eigenvalues on the homology, even though and I want to think about how can I generalize that? What does this mean? And what would it mean for these Smale diffeomorphisms? So I thought for the Smale diffeomorphisms, well, you do have these filtrations still. So you have some kind of filtration, and in the filtrations, you're going to build homologies, you're going to again compute the homology of the manifold, and now you have a map that preserves the filtration. And so maybe the same theorem is true. That if you look at any eigenvalue in the homology, at least the periodic points have to grow that fast. So if these were 0, no growth in the periodic points, the eigenvalues modulus 1, so their logs are 0. Finite periodic points, logs 0. I want to say now, the log is not 0. Periodic points are growing at least as fast as e to the log of the eigenvalue. So I want to say basically you have an eigenvalue modulus k, you have k to the n periodic points of period k, independent of whether or not it could be canceling out in the left shoe. So that was going to be the analog of my result for those systems, even though I couldn't prove it yet at the time. But I wasn't happy because it was special. These systems aren't general. And so then Rufus Bowen was working on various concepts in dynamical systems, and he had proven that this growth rate of periodic points for these systems was the same as the topological entropy of the maps. So now topological entropy is general for all maps, so I ultimately made a conjecture. It was a little bit colored by some other work I'll tell you about in a minute. This conjecture says, said if f and n is C1, then the topological entropy of that is bigger than or equal to for any eigenvalue. Now I had a general statement. So the entropy is a measure of the chaos of the map. It says, I'm not going to write down the formal definition. It says if you want to look at orbits, how many orbits can you detect if you have only can look up to epsilon? So you now look at orbits up to epsilon. You say, how many do I have? I fix epsilon, I let the iterates go to infinity, I ask for the growth rate of that number, and then I take the largest growth rate I get as I let epsilon go to 0. So in some sense, it's, if you were going to give the symbolic description of the orbits of this dynamics, and you're only going to give a description up to epsilon, how many symbols do you need to be transmitting this information? And that number is the topological entropy of the map. It's not 0, it means you've got chaos. It means you've got, to transmit even the number of orbits you've got to do something very complicated. So that's the conjecture. It was a little tricky because it's false C1, I mean C0. False C0 ellipsis, even piecewise linear, is false. So here's the natural example. take theta goes to 2 theta on the circle, and you suspend it. That gives you a map of the 2 sphere of degree 2. And now you compose this with a little push up from the south pole to the north. You can actually give a formula for that. Actually, in polar coordinates, it's theta r. And so the degree is 2, but the entropy is 0. Because there's no recurrence. Everything's just going up to the north, so after some while you just keep printing North Pole, North Pole, North Pole, and there's nothing to say. So the entropy is 0, but the homology is log 2. So that's the count. And then you can make a PL version of that and homeomorphism of the format. So what's known? What's known about this conjecture? Yes, for C0 and H1 or pi 1, where you look at the growth rate of elements of the fundamental group as you iterate the map, just map of the fundamental group, and you take that instead of eigenvalue. This is true. This was Manning, and this was maybe Bowen, maybe Gromov. And then it's also, yes, for total maps.
So what's the hypothesis on the H1 or pi 1?
It's a group, finitely generated. So it's a fundamental group of a manifold or homology group of a manifold. So a finitely generated group. For the homology group, you can take the eigenvalues as I did before. For the fundamental group, you define a notion of growth rate. So you pick the generators, you pick an element, and you ask how long a word do you need to express f sharp to the n of g. And this word length will grow. If it grows exponentially, then you take the growth rate of that number, and that's the lower bound for the entropy. Total homomorphisms, it's also known. I think the linear ones minimize the entropy, and they're right on with the homology. So it's okay for total homomorphisms. It's okay for some nil manifolds, I believe. And there's a question about whether or not you can actually go, you take the subalgebra generated by the first homology group. It may be true that you look at the eigenvalues on that subalgebra, that's a lower bound for the entropy, even in the C0 maps. I gave false proofs of that several times in my life already, but I think it's a nice open problem. Okay. Then, the big result is Gándara. Conjecture is true for C infinity F, or C infinity F. And now it's really, I find that it's really quite an amazing theorem. It says you have a lower bound for the entropy for the whole homotopic class of the map. And it's given to you by a simple topological invariant that's calculable. The entropy in principle requires infinite iteration. So, but it's still open. So that's what has sparked my interest again. That's why I got back to thinking about this after all these years of working in complexity theory mostly. I was chair of my department, which was a terrible thing. And so I just recently got to be unchair. And so then I could focus again. So somehow I had a postdoc who was ambitious. And she wanted to prove this. So it got me re-involved. So I've been obsessing about it. The other thing that's true here, it's also true for all these axiom no cycle. These original diffeomorphisms that were supposed to be are omega stable in C1. So it's true C1 which is when I imagine that it was true, and that came into the C1 part of the conjecture. This was proven by Bob Williams and myself and Ruel and Sullivan. So there's some evidence that it might be true C1. All right. So I already told you that for these axiom cycle diffeomorphisms that emit a filtration. So what happened, so Smale's proof went like this. He said, well, take your handle decomposition for the manifold. Now look at the handles. Now use the transversality theorem to make the diffeomorphism transverse to the handles to all powers. Once you do that, he says, okay, let's look at the filtration. Now they're transverse. Push the behavior down to the things below that level, except for what happens here. And make those expanding, and that means you now have an axiom no cycle diffeomorphism, and you can even possibly be transversal, so that's the isotopy. You build it by the transversality theorem. And then so let me I think quickly thereafter, I realized you could do that densely just by picking a very fine triangulation of the manifold, now moving the zero cells into a neighborhood of the zero cells and one cells into a neighborhood of the one cells just by the same trick. So in fact, you could see that the structurally stable diffeomorphisms are actually C0 dens in the space of diffeomorphisms. Not C1 dens, but C0 dens. And once you did that, you thought about it, suddenly you have the chain, the simplicial subdivision gives you a natural chain complex for the manifold. And you've just exhibited what the diffeomorphism does to the chains. So, in fact, so there's the density theorem, and then with Sullivan, we formalize this a little bit better. So you're given, and producing a diffeomorphism, there is a chain complex for the manifold and an endomorphism. So now I've got 0, 0, 0, m, 0, 0, 0, 1, etc. This is endomorphism. This endomorphism commutes the homology of the map. And moreover, the entropy of F is equal to the max log eigenvalue of, I'm going to put here. Take this matrix and you take the absolute value of every entry. And now the eigenvalues likely go up, and the entropy is given exactly by the log of those eigenvalues. And then the theorem goes on, analogously to the H-coordinate theorem. Moreover, if mention and maybe these are let me put a I'm going to add a word here just to make sure that I'm formally correct. These are the fitted ones, and they're the ones that we constructed with our bare hands. But it's probably true for all of them. The entropy conjecture is true for all. So moreover, if mention n is bigger than equal 6, and power 1 equals 0, then here. Then given it arises from an example. After a given one, the homology of the complex is right. The induced map on the homology is right. Then you actually can produce a diffeomorphism in that category. And it has that entropy. So the last, I still do have 5 minutes. So the last thing I want to touch on is how good is this entropy conjecture? So now you've got a theorem. So I'd like to know, given this number, given the map on homology, what's the best complex and endomorphism you can find? Can you find one where the limits of these eigenvalues converge to the limit to the eigenvalues of homology? So in other words, I'm asking, conjecture gives a lower bound on the complexity in the whole isotopic class. You can make examples. Can you make examples that converge to this lower bound? Or is there something else? Is there some more information that would force more chaos that's not visible immediately on the homology? And so the one case that problem, which I've just said without writing, is what Morse-Smale diffeomorphisms. So you see what happens in the Morse-Smale diffeomorphisms. These handles can get permuted, and also they make reverse orientation. So what happens is the Morse-Smale, so let me here. You can find the endomorphism to be of the form J, has some star here, has some zero, where the PI are sign permutation features. That is, you could have a -1. For example, this. Maybe one handle, reverse orientation when it came around. The others preserved it. This gives you the map on the relative group. Now these, of course, all have eigenvalues 1. When they're reduced on homology, the same, because it's a quotient. This star thing is because you could have that type of behavior between the eye handles, where one is accumulating on the other in the steps of the filtration. So now the question arises, suppose the map on homology only has roots of unity as eigenvalues. Can you find an endomorphism where each BI is this kind of, we call them virtual permutations? Because the virtual permutations are stars. So Dennis, being a very educated mathematician, says, okay, we're going to have make a K0 of the ones which have eigenvalue roots of unity, we make another K0 of the ones that are virtual permutations. We take a quotient group, and we take the alternating sum of the maps on homology in this quotient group, and in order to do this, you'll have to have that goes to 0 in the quotient of the K0. And then John Franks and I proved if it goes to 0, you can find it. So the abstraction is everything, and then the question was, is that group 0? And the answer is the group is not 0. The group, and Hendrik Lenstra proved that the group is not 0, and in fact, if you look at the matrix that represents the 23rd roots of unity, but is not conjugate to the usual matrix, that one is non-zero in the class. So here's the question. Suppose you have eigenvalues, roots of unity. You want to know, can you find diffeomorphisms whose entropy tends to 0? And in fact, you may want to know how good you can resolve these matrices, and when you take their absolute values, you don't get a big eigenvalue. So you have a matrix with eigenvalues, roots of unity. Now you ask the resolution of it, which would be some complex which commutes the homology and that map in dimension 0. But when you take the absolute values of the entries, they're small. That's the question. And in fact, you can do it now because you have the specific matrix. It's a 22 by 22 matrix. So you can imagine you take a ball and add on 22 handles. Dimension 2, so this pi 1 is 0. So here you got it. You got a manifold with boundary, but you've got a map on homology, which you know has eigenvalues. Roots of unity, but you can't make a Morse-Smale diffeomorphism. What's the best dynamics can you do? So I think the general question, and even that particular one, are very fine open questions in relations between dynamics and topology, and of course this whole entropy conjecture and lower differentiability is another one. Oops, I ran 2 minutes over, sorry, thanks. I think I said everything I meant to say. Thank you.
Thanks, Mike. Are there any questions?
I didn't recognize the statement of the H-cobordism theory, the theorem, and it had no cobordisms in it. Is it easy to see that that's equivalent?
I have to admit, when I read Schnamer's paper, it was very difficult, especially in the point rate conjecture. Milner's book is a lot better reference for my paper. So, but there is a kind of dynamics theorem in the middle. So the dynamic situation is if you have a point of index I, and you have a point of index I minus 1, and there's one orbit connecting them, then you are in a situation that is typical in 2 dimensions. It's a saddle node. Saddle node. The saddle node looks like this. There's an expanding point, and there's an attracting point. And then this is a totally attracting point. So the index is 1 and 0. But now you see what you can do is you can simply make these things collide along here dynamically and just end up with no periodic, no 0 at all. You just get a flow along the line. And you contract towards it in this direction, but there's no 0. So the proof of the H-cobordism theorem is done in Milner's book essentially says, okay, if you can reduce the situation to the I handles intersecting the I minus 1 handles, intersecting like this, then you prove the H-cobordism because you cancel all the handles. But the way you can see to do that now, in either the Morse-Smale case or this, is you're given the chain homotopy. So the chain homotopy tells you how to lift the I handles over the I plus 1 handle to change the boundary map. So the boundary map is an isomorphism, you change it by this chain homotopy, and then you make it equal to 1 everywhere, and then you wipe them out. So it's the same, I think, essentially it's the same proof that says, okay, if you produce the right homology everywhere, you use the chain homotopy to change the number of intersections.
Questions?
Do you know if, I mean, in the classical cobordism theory, there are counterexamples in dimension 4, I know that's not right, but there are H-cobordisms that are not trivial. And do you think that
there is a simple homotopy version of this theorem that's due to Mike Mauer, who was a student at CUNY. I mentioned that. Mike Mauer. Simple homotopy. And then there was, I should have mentioned that the theorem is true true for C1 and degree, and that's the theorem of Mishurevich and Shutitsky. I won't dare to try to spell their name. Mishurevich and Shutitsky. Around the early 70s. So, does that answer your question, more or less? I'm not a topologist. I haven't tried.
I think the question was cases where there's no H coordinate there
Right.
topologically. What's the dynamics?
Yeah, I don't know. Actually, I don't know. I think in the case of Morse-Smale systems, Mauer proved the characterization like the one we have, but only when pi1 is a simple homology for pi1. If you have a counterexample, it means it's not in that framework, and I don't know, I never thought about it.
Another question. In your theorem of Sullivan, did I hear correctly that it involves the eigenvalues of the matrix whose entries are the absolute values of the...
Yes.
That seems like an unusual operation on matrices to take the absolute value of each entry. Can you say a little bit about how it comes up?
So suppose I have a horseshoe, and it maps this one, this one through like this. So then I can think I've had a map maybe from one handles to one handles where they go through like this. And some give me +1, some give me -1 because the orientation has been reversed on the transversal. But dynamically, there's no difference between this and going through 3 times, constantly preserving the orientation. Dynamically, you don't know what's going on out there. So you just know you have 3 strips that are mapped across one another, and that gives you, the entropy has to be then the log of 3, or something like that, but you don't know the signs. So that what we've done is we've actually taken some things and we've made them cross, and we can count in the homology by looking at the sign of the intersections of the unstable manifolds with the local stable manifold. So that will tell us the map on that level, but dynamically, the complexity you're getting doesn't recognize the orientation. So we take the absolute value.
If you have more than one map, for instance, if you have an integrated function system, you can still define the notion of entropy, and you can still look at the action on homology, the semi-group action on homology. Do you know whether there is a counterexample to the entropy conjecture in that setting?
I would think that you need some compactness on the family of functions that you're iterating in order to get a good handle. Here's how the proof goes. I'll tell you Yamdin's proof. Yamdin proves the theorem by saying, if you look at a disk and you iterate a disk, its volume of the k-dimensional volume of this k-disk can't grow faster than the entropy. That's the proof. So then you say, okay, if the volume of a disk can't grow faster than the entropy, if I fix a cycle in a differential form, then the integral of this differential form over the iterates of the cycle can't grow faster than the growth of the volume of the cycle, which is bounded by the disks, finite number of disks. So that proves the theorem. And how you prove that is, if the points are staying close in the map to C infinity, now you approximate by a polynomial, and then you use estimates that say that it's like complex variables, or you can estimate the derivative by the C0 size on a circle. Here you say, I can estimate the coefficients of the polynomial by the fact that the C0 size is small because this disk stayed inside a disk of a certain size. So, and then you resize it back to unit and you go on. So what you're saying is, how many things, if they stay close, I can approximate by something essentially flat. And then I do it again, again, and again. So for that, you need some kind of estimate that's uniform. So I think if you just have an iterated function system with no bound on the sizes of anything, you would probably have difficulty proving the theorem this way. But if you had some kind of compactness on the family, probably the same type of argument would work. What you have to do is look at, Gromov gave a proof of the theorem, which was probably the best, and it was in the Bourbaki seminar, probably in the end of the 80s. So look for Bourbaki and Gromov and his proof. It might generalize to that. I don't know, I haven't tried.
Okay. You gave the dates for
For some of them,
all the stuff.
40, 50 years old.
What about the new results?
No, these results all date from the result with Franks, which I didn't write, is from the 80s sometime, and Lenster's results is from the 80s. Bass worked on the problem too from the 80s. The other results are all from this, Janden's results is from around 85. The other results are from the 70s.
What about
This one's from the 70s. Yeah. Yeah, so things are, yeah. I don't know how much, I just got a paper referee about the fact that the entry is bigger than the log of the degree. For some other smoothness types of functions that have to do with Sobolev spaces that are way beyond me. So there's still some work going on, but I don't think there's been work going on the question of trying to get the absolute values of these matrices eigenvalues to be close to the homology eigenvalues, and not even in the special case of Morse-Smale systems on simply connected manifolds. It's a purely algebraic, I mean, it would seem like it's a purely algebraic question. But I don't have a clue.
There are no more questions, and we thank speakers.